Hello. So I thought today I would just do a bunch of problems at the back of the book, or at the end of the chapter rather, for chapter 2, just to try to put together all the concepts that we have been talking about. So I will not recopy most of the problems down, I will just read them out loud. So these are the book questions, and I'll tell you which questions they are, so you can follow along. And this starts on page 31 of the book. And the idea is that this entire lecture is just going to be problems, so watch as many or as few as you would like. The first one I'll do is from the questions section. So we'll just start with question 1. This is a figure that gives the velocity of a particle on a one-dimensional x-axis. What are the initial and final directions of travel? Does the particle stop? Is the acceleration positive or negative? Is it constant or varying? So let me recopy a drawing of it of sorts. The idea that here is the velocity. I think we've been using green for velocity as a function of time. So in this case, the question is, is that, you could think of this again, try to think of what this means. There's some one-dimensional coordinate system that some observer has laid down that has some origin, and they've defined some positive direction and some negative direction. So the way I drew it, we can think of negative as to the left, positive is to the right. It could have, it could have, since it's one dimensional, it could have, positive could have meant into the air, negative could have meant towards the ground or up the ramp or down the ramp, whatever. But let's just take negative is to the left, positive is to the right. So in this case, I would look and see, okay, what is the particle doing? It starts less than 0. It starts with negative values, negative velocities. It looks like there is some point where the velocity equals 0, and then beyond that, the velocity is positive. So again, what does that mean? Again, remember, since velocity is what we're calling a vector quantity, the sign of the velocity is telling you the direction. So in the case where the velocity is negative, I'll highlight that in green here. That just means that the velocity, a negative velocity means it's moving to the left. This point here where the velocity is 0 would be a point where it is momentarily stationary. Then this remaining part, once it becomes positive, means it is moving to the right. You're just reading the value of the velocity is telling you the direction it is moving in. And the actual number, if we were to assign numbers to the vertical axis, we could also interpret, that would give you, say, it's moving, say, negative 10 meters per second, then it goes down to 5 meters, negative 5 meters to negative 2 meters to eventually 0, and then positive 1 meter, 2 meters, 5 meters, 10 meters per second, whatever. So is the acceleration positive or negative? Is it constant or varying? Well, we just explained that the velocity is changing. So that means the acceleration is non-zero for one. And now we can ask, is the acceleration positive, negative? So then we can think conceptually, what is acceleration? How does acceleration connect to velocity? Acceleration is how the velocity is changing with time. or graphically, acceleration is the slope of the velocity curve. Or to use calculus speak, the acceleration is the derivative of velocity. You know, I can even write that down. Acceleration, remember, is the derivative of velocity with respect to time, which just means the slope of the v as a function of time curve, which is saying the rate v changes. In this case, the slope appears to be positive and constant. I could pick 2 points. I could find a rise over run. Since this appears to be a straight line, we know straight lines are defined by having a constant slope. So I would say A is positive and constant. And again, positive means that, think back to, I think it was the previous lecture, we talked about that positive acceleration means that no matter what the velocity is eventually doing, given enough time, the acceleration will try to make the velocity point in the same direction. And this is actually a case where that occurs. Trace this out as a bunch of arrows and dots. The acceleration is positive in constant, so we would say that the acceleration might look like this in the 1D coordinate system. Initially, the velocity is moving to the left. It has some negative value, but then at some later time, it has a slightly smaller value, eventually a very small value, momentarily stops, and then the velocity has a positive value as time goes on. So this would be a case where the velocity turns around and ultimately becomes parallel with the acceleration. Question 3. This figure shows 4 paths with objects that are moving from a starting point to a final point, and all of them move to that same time interval. The paths pass over a grid of equally spaced lines. Rank the paths according to their average velocities and average speeds. So let's see. So those are not quite equally spaced, but let's pretend that they are equally spaced. And then it looks like there's one goes over here, turns around, and then ends up here. So that's number 1. Number 2 looks like it starts here, goes over here, turns around, and ends up here. It's 2. 3 looks like it starts here, ends up right here. And 4 is something like that. And the question is, so the idea is that there is some distance here, which is the same as this distance, which is the same as this distance. And each of these paths occur over the same amount of time. So we could just give it a number to make it simple. We could say 1 minute. Over 1 minute, the 4 objects or the 4 people here traverse the path. So in 1 minute, just to find some easy examples, in 1 minute, person 3 looks like they travel much less of a distance than, say, person 1, which goes way to the right, turns around, and goes left. But the question is, the average velocity is what? We could think of the definition. Average velocity is defined as the displacement over the amount of time. And since each of these occur over the same amount of time, If we were to rank their average velocities, that just means we need to rank their displacements. All same delta t. So displacement, meaning final minus initial, we're not looking at how crazy and loop-de-loopy their paths are. We just are looking at the start point and the end point. And if I look at all these, they all start at one line, and no matter what they do, they all end up one line to the right. So even though some of them, have zigzags along the way, ultimately they all have the same displacement. Take object 1 for example. Starts here and ultimately ends here. It moved over one grid line. This one starts here, ultimately ended here, moved over one grid line. Starts here, ends here, moved over one grid line. Ultimately starts here, ends here, moved over one grid line. So they all have the same delta x, which means they all have the same delta v. And yes, I realize my screen has stopped sharing. Or they all have the same v average, rather. This only seems to happen in my apartment. This never happens when I recorded on campus. So in this case, I would say they all have the same average velocity. And now what about the average speed? So your book uses S for speed, and that's defined as the total distance over delta t. Now again, they all have the same delta t, so now it's a question of which ones traveled a greater distance than the others. So there I would say that the average speeds, it would be 4 traveled the farthest, and that average speed must be greater than, say, 1, which is the same as 2, which is less than 3. So in this case, right, the fact, if you look at the path that 4 took, if they have to do that entire thing in 1 minute, they better be moving a lot faster than person 3, who has to cover much less distance in 1 minute. That's a nice example of how to distinguish between speed and velocity. This graph is more involved, so I drew it in advance. So this is question 11. Question 11. This figure shows a particle moving on the x-axis, undergoes 3 periods of acceleration. Plotted is the acceleration as a function of time. Without doing any computations, rank the acceleration periods according to the increases they produce in the particle's velocity greatest first. So there are these kind of 3 moments of, which I'm calling capital A, capital B, capital C, where a particle experiences a non-zero acceleration. During region A, it looks like it goes through some sort of intermediate acceleration for 2 units of time. In time period B, it goes under a lesser acceleration, but for a longer period of time. And then at moment C, it goes through it experiences a very large acceleration, but for a very short amount of time. And the question is A, B, or C producing a bigger change in the particle's velocity? So how is the velocity changing given this acceleration? And here we have to bring back our other idea from calculus, where the derivative connects in variables in one direction, the derivative of position is velocity, the derivative of velocity is acceleration. And then going the other way, the change in velocity is the integral of the acceleration over time. And again, what did that mean geometrically? That just means the area under A of t over a given time. So how is velocity changing? I just look at the total area underneath the acceleration curve. If there's a large area, that's a big change in velocity. If there's a small area, it's a small change in velocity. So in this case here, the grid given makes it simple for us because I can compute areas just by essentially counting squares. So if I look at A, there looks like there's 8 squares. B also has 8 squares. And C, there's 1, 2, 3, 4, 5, 6, 7 squares. So the area of A equals the area of B, which is greater than the area of C. So as a result, the change in velocity for A is equal to the change in velocity for B, which is greater than the change in velocity for C. Those intervals A and B produce the same change in your overall velocity. One just does it over a shorter amount of time, so there's a larger acceleration with a shorter amount of time. B has the same net effect, it's just spread out over twice as long. Whereas C produces almost the same, 7 is close to 8, almost the same change, but not quite. Again, the idea of this is connecting acceleration, velocity, and position in the opposite direction through the integral, which is a fancy word for sum or area under the curve. Sum of all, sum of a bunch of tiny rectangles. In this case, it's just 3 big rectangles, so it's actually easy to do. Question 8. The following 4 equations give velocity as a function of time. To which of these situations do the equations of table 2.1 apply? And table 2.1 is essentially the equations of 1D kinematics with constant acceleration. Let me copy them down. A v of t equals, it's just a number, right? 3. I would poo-poo a little bit on the book because they did not give units. We're going to assume they mean meters per second squared, say. 3t minus 4. Then d is another parabola. Yeah, 5 to the minus 3. And it's asking, do these equations apply? Or I'd say another way, are they valid? If these functions velocity. Also, I'll note that the table has 3 additional equations to the 2 I derived. Looks like it's equation 2.16, 17, and 18. These equations are nothing new. The 2 equations I derived and will highlight here are the only 2 you actually ever need. Those are the 2 fundamental equations. The other 3 that are listed in the book are just algebraic manipulations of the 2 I've highlighted. You can use algebra to get rid of one of the variables. Like you notice one of them doesn't have time in it. So essentially what they did there is they solved one of these equations for t, and then they plugged that into the other equation so that equation was a bunch of symbols that did not include t. Or similarly, eliminating acceleration or eliminating what looks like the initial velocity. I will never really reference them because I like to just think of these two equations because these are kind of the more fundamental. But sometimes algebraically, it's helpful to use one of the other two or one of the other three equations. Sometimes it comes up in experiments. Like if you're doing an experiment, it depends, there might be certain variables that are easier for you to measure in an experiment. So if you can manipulate the equation so that variables you don't have measurements for are gone, you can then use those equations. But again, they're just algebraic manipulations of these two. But again, the rule, oops, my highlighter's still on. The rule is that A is a constant in order to use these two expressions. If A is not a constant, you better not try to use these equations in a problem. So really, this question amounts to us going back and again, this equation amounts to going back and asking, is the acceleration constant as a function of time? If it is, we're good. If not, then we have to go back to the drawing board. I do not want to stop and restart this lecture, so I'm trying to an alternative method here. All right, we're gonna plug my iPad in and see if that does a better job. Presumably, if it goes through a wire, that is more stable, right? Who the heck knows? So for question 8, if we had, when you learn how to take derivatives, knowing that acceleration is derivative of velocity, you could do this mathematically and just write out the derivatives for each of these expressions. What we will be doing instead is looking at plots of them and assessing whether or not they have constant slopes. If they do have constant slopes, then we are good to go, because then that means that the acceleration is indeed constant. What a mess. I'll record a lecture from home. Yeah, whatever. So looking at A, and I'll do these all kind of roughly the same plot. Looking at A, V equals 3, so that might look something like this. B, the highest thing is t squared, so that's a parabola. The thing in front of the t squared is positive, so that's going to look something like this. C, that is the equation for a straight line. That is going to look something like this, maybe. And then D is also a parabola, so that might look something like this, maybe. So, what do these have a constant acceleration? Again, what is acceleration in terms of velocity? Acceleration is the slope of the velocity curve. For A, I would say we're good to go, because in this case, the slope equals 0. So then the acceleration is indeed a constant of 0. Similarly, for C, I would say we are good to go. It is a straight line. The slope in that case is a constant. The slope is constant, and I guess in this case, greater than 0. For B and D, however, notice that the slope, if I were to look at, say, a tangent line, that tangent line is changing directions as you go forward in time. It starts shallow and becomes steeper and steeper as time goes on. So the slopes are changing. So if I wanted to use the kinematics equations, I would run into trouble with B and D. But for equations A and C, we're good to go. And those equations do apply. All right. Problem 3. Let's take a look at that. So problem 3, this over here. Compare my answers so I don't have to do math over again. So problem 3, where are we? An automobile travels in a straight road for 40 kilometers at 30 kilometers per hour, and then continues in the same direction for another 40 kilometers at 60 kilometers per hour. What is the average velocity of the car during the full 80 kilometer trip? Assume that moves in the positive x direction was the average speed, and make a graph. So in these sorts of problems, we actually have to do some numbers. It's good to start by writing down what we know. It travels 40 kilometers at 30 kilometers per hour. And 40 kilometers at 60 kilometers per hour. And it's asking for the average velocity. Now, it might be tempting to say, well, the average velocity, the average between 30 and 60 is 45, so the answer is 45 kilometers per hour. But unfortunately, that does not quite work in this case because it is moving at those two speeds for different amounts of time. If I know that you travel 40 kilometers at 30 kilometers per hour, we could figure out how long that part of the journey takes. In this case, this part of the journey, 40 kilometers divided by 30 kilometers per hour gives us, since we're moving at a constant rate, you could think, where is this coming from? You could think, if I'm traveling 30 miles per hour, after 1 hour, I travel 30 miles, after 2 hours, I travel 60 miles, 90, etc. So what I'm saying there is that the distance is the velocity times the amount of time. Or I could even say to use displacement, we could use delta x is our constant velocity times time. So I could just then solve for t, which is then just displacement over velocity. So then this is 4/3. I usually won't go this careful with the units, but I'll just do it runs real quick, just again to remind ourselves. 4/3, because that's 40 divided by 30. Then you have kilometers divided by kilometers per hour. I could think of that as kilometers divided by 1 divided by kilometers per hour. So that's the same thing as 4/3 kilometers per 1 times hour over kilometers. Kilometers cancel. I'm indeed left with a unit of time as expected. It takes me 4/3 of an hour to do this part. So we'll call this leg A, and then this leg B. So then B, what is that instead? You're again going 40 kilometers, but now you're going 60 kilometers per hour. Twice as fast, ends up being half as long. You travel that amount of the journey in 2/3 of an hour. So while we didn't need to necessarily do that, I guess we did. So then we could ask then the total time, how long did the entire journey take? 4/3 plus 2/3 of an hour, or 6/3 of an hour, or 2 hours. So if I were to plot this is 1 hour, this is 2 hours. Separated by thirds, this is time, hours. And then I'm plotting, I guess, distance. And then we can call this 40 and this 80. So let's see, at this point in an hour and a third, I go out to here. And then to get to 2 hours, I go to here. So in 2 hours, I travel 80 kilometers. The average velocity is the total displacement divided by the total amount of time passed. So in that case, I would say it's 80 kilometers was the total traveled over 2 hours. In this case, the average velocity then becomes 40 kilometers per hour. Not 45. And again, how is that seen graphically? Remember this average velocity. If I connect the start and the, oops, I missed. If I connect the start and the end point by a straight line, I missed again. Let me start at the end. If I go, there we go. If I connect the start and the end point by a straight line, this straight line is the slope. That slope equals the average velocity, which is 80 divided by 2, which is 40. Let's see. Average speed I don't care about. In graphs we did. I guess that's enough. All right, how about problem 7? There was an order I wanted to go in. Do 30 first, all right? We're doing 30 first. Problem 30. Problem 30. Oh, I have an augmented version of this. So this is, if you're going too fast and you see a state trooper, by the time, how long does it take for you to get under the speed limit? Okay, so let me recopy from my notes. So suppose you are driving 85 miles per hour in a 55 mile per hour zone. Typical cars, on a typical car, you can decelerate at a rate of about 11 miles per hour each second. So the question is, you're driving 85 miles per hour in a 55 mile per hour zone. You notice a policeman and you slam on your brakes. Your brakes give you an acceleration of negative 11 miles per hour each second. How long does it take you to get under the speed limit? So here's an example where we can use our kinematics equations and where we can kind of write this out a little bit more explicitly. So I always like to start by drawing a picture. Here's the car. It's initially going at 85 miles per hour. The police officer notices you and you try to slow down at some point, ending going 55 miles per hour. And the question is, how long to do this. So I would start by saying, what do we know? Are there any numbers that we could commit to variables? I prefer to work in variables as long as possible and to plug in numbers only in the absolute last line of work. Else you run into the risk of making math errors all over the place. So I would say we know our initial velocity is, and actually, we should take a step back. We should throw down a coordinate system first. So let's throw down a coordinate system where this is the origin and the positive direction is to the right in the direction the car is moving, and the negative direction is to the left. Why do I need to know that? Because then I can say my initial velocity is plus 85 miles per hour. And then my final velocity is plus 55 miles per hour. So the car is still moving to the right, it's now moving at a slower rate. And the acceleration, since this is meant to slow you down, the acceleration has a negative value of 11 miles per hour each second. Every second, your velocity changes by negative 11 miles per hour. And then we want to know how long this takes. We don't know that. So I'll put it as a question mark just to remind myself what we're ultimately looking for. All right, so the question is, I know how velocities are changing with an acceleration given a time. If I look at the two kinematic equations, and by the way, to point out, make a note to ourselves, the acceleration is a constant, which is key because I'm about to say, it looks like the kinematic equation v equals v naught plus at might be helpful in this. Some velocity at some later time, which I'll call the final time, is equal to the starting velocity plus some acceleration times time. And I could ask myself, what in this equation do I know? I know this, I know this, I know this, I don't know this. But that's great because we have one equation and there's only one variable that we do not know. So algebra allows us to then solve for the answer. So then I might say it's v final minus v naught equals at. Notice I haven't plugged in any numbers. And this is vf minus v naught divided by a equals t. Now t is written in terms of everything that I know. Let me just steal the answer. So if I plug in numbers, 2.73 seconds. So I'll highlight it, and I'll highlight it in red. Life lesson. If you're speeding, you will get caught. Even if you slam on your brakes and have the highest acceleration possible, looking at this here, it still takes you almost 3 seconds to get down. If you see the policeman, they see you, and they're probably going to clock you at too high a speed in the next 3 seconds. So don't speed. If you take away anything from this course, don't speed. Question 7. Two trains, each having a speed of 30 kilometers per hour, are headed at each other on the same track. Yikes. A bird that can fly 60 kilometers per hour flies off the front of one train when they are 60 kilometers apart and heads directly for the other train. On reaching the other train, the crazy bird flies back to the first train, and so forth. What is the total distance the bird travels before the trains collide? So this one There are a couple ways I could think of to solve this problem. One is very lengthy. There are some tricks that can be used. So we have two trains, they're moving at the same speeds, but in opposite directions, so they have opposite velocities. And then there's a little bird that is flying from one train, and then once it gets to that train, it flies back to the other. That train has moved, and then it goes back and forth until eventually the trains collide. And the question is, how far does the bird travel? Now, the hard way to do this could be that you could calculate how long it takes the bird to get to the first train. Or let's say, let me give these trains some names. Let me call this train A, this train B. Well, B, bird starts with B. Let me call the bird B, and this I'll call train C. So one way you could do it is you could calculate the amount of time it takes for the bird to get to the train C. Then calculate how much extra time it takes for the bird to go back to A, and then how much time it takes from it to go to A to C, C to A, et cetera, et cetera, et cetera, and keep doing that until the trains run into each other. But the insight here is that A, B, and C are always moving at the same speeds. So if I want to calculate the total distance the bird travels, since its speed, not its velocity, is constant, there I would say the speed of the bird is always 60 kilometers per hour according to the problem. Now I'm saying speed here because sometimes the bird is flying towards the right, sometimes it's flying towards the left. So its velocity will be either positive 60 kilometers per hour or negative 60 kilometers per hour. But speed is always the same. So then the total distance in that case is going to be the speed of the bird times the, I'll call this capital T with a swoosh, total time flying, say. And the nice thing is that this is what we want. We know the value for this. Unfortunately, we don't know the value for this. If we could figure out big T, then we'd be done. But we have two other things in the problem. We have the two trains that are on a collision course from one another. So what we could ask ourselves is, and their velocity, they're in this case, not only their speeds, but their velocities are never changing either. They're always moving toward each other. So we could calculate how long it takes for the train, and another thing to say is that the bird is not affecting the speeds or it's not affecting anything about the trains. So we could treat the trains as if the bird wasn't even there and just ask ourselves, how long does it take for the trains to collide? That will give us big T. We could then go back, plug it into this equation to get the total distance the bird travels. So let us do that. So here for the train, so we're going to how long for collision of trains. Now here, it's helpful to be very explicit about our coordinate system. Or rather, I think this is a good problem to practice with drawing down a coordinate system. And I'm going to choose my coordinate system where this is the origin, and this is going to be the positive direction. I'm going to choose it so that the first train A, starts at the origin, which then makes train C, start at 60 kilometers to the right of the origin. So with these sorts of problems, it's worth writing down what we know. So train A, what do we know? The initial velocity of the initial position of train A is 0 kilometers. It begins at the origin. The initial velocity of train A, which actually just equals the velocity of train A, is in this coordinate system plus 30 kilometers per hour. The plus sign because it's moving in the positive direction towards the right. Train C. The initial position of train C is plus 60 kilometers. The initial velocity of train C, which is just actually the velocity of train C, because it's not a change in speed in any way, it's not accelerating, is negative 30 kilometers per hour. Negative, it's moving towards the left. We could say neither is accelerating. A for both is 0. So what that means, A is 0, which is a constant. So I could use the kinematic equations for both of these trains. I could write down the position of train A as a function of time is the initial position of train A plus the initial velocity of train A times t plus 1/2 the acceleration of train A times t squared. Since the acceleration is constant, this would be valid, but it's even better for us because the acceleration is not only constant, it's 0. So that all just goes away. So in this case, it's the position of A plus the velocity of A times t. Or again, notice I guess we could even be, in this case, it's even, I like to plug in numbers only at the very end unless the number is 0. So in this case, since the initial position of train A is 0, I could just write this as the velocity of train A times t is the function that tells us position as a function of time for A. And then for C, it's the initial position plus 60 kilometers plus the velocity of C times t. But remember, the velocity of train C is a negative number, so the position for train C is going to constantly be getting smaller as time goes forward, where train A is getting positive as time goes forward. We could even graph this if we wanted to. And they're both moving at 30 kilometers per hour, so train A might look something like this. Train C might look something like this. This is t, this is x. And that is this t that we're curious in, because this would be the point where they collide, or they're at the same position on the track. So graphically, then that kind of gives us some insight of what we need to do. We're asking, when does the position of train A equal the position of train C? And actually that occurs at some time t. We could even rewrite that, but that is actually the time big T that we're looking for. So then I could just write this out. VOA T equals XOC plus VOC T. And again, it's always good to kind of assess what we know and don't know. I know this number, I know this number, I know this number. I do not know what T is. But since I have only one equation with one unknown, I can solve for it. So in this case, I might say VOA minus VOC times T equals XOC, or T equals XOC divided by VOC. And then again, I'll be explicit just because some of these have XOC was the initial position of train C, so that was plus 60 kilometers in the numerator. The initial velocity of train A was plus 30 kilometers per hour minus the velocity of train C, which itself was negative 30 kilometers per hour. So then this ultimately becomes 60 kilometers divided by 60 kilometers per hour, or 1 hour. They will collide with each other after an hour. So, what a treat, because we ultimately wanted to find the distance for the bird, which was the speed of the bird times this t we just found. Speed of the bird was 60 kilometers per hour times 1 hour equals 60 kilometers. So ultimately, this was the answer the problem asked for. But notice we had to find some intermediate things along the way. '69. There is a graph goes out to goes down to 12. T in seconds. It says that it says this is 8. Yeah, this value is 8, so that's 4. This is a velocity, so meters per second. And it's saying somewhere, how far does the runner whose velocity time graph is shown in this figure travel in 16 seconds? The vertical scaling is set so that the top is 8. So this is velocity. It wants how far does the person travel in these 16 seconds. So I guess I should say this is 4, 8, 12, 16. Now again, the connection between position and velocity is that the derivative of velocity, the derivative of position is velocity. The integral of velocity is position. So the calculus relation is that this is equal to the integral of velocity, or again, the area under V from t equals 0 to t equals 16 seconds. That will give us the total displacement that this person undergoes. So we have to just calculate the total area under this curve. Now, conveniently, the curve itself can be broken up into various familiar geometric shapes. if I draw some dotted lines here, a dotted line here, dotted line here, dotted line here, dotted line here, then you might notice that, say, there's a big old rectangle here. Rectangles are pretty easy to find areas of. There is a skinny triangle here. Triangles are also pretty straightforward. There's a rectangle here. There's a triangle here. There's a triangle, and then there's a rectangle here. So if I just find the areas of all these shapes and add them all up, that gives me the area under the entire curve, which by the connection between position and velocity gives me the total displacement. So for example, that first little red rectangle, its area looks like it has the area then is 1/2 the base. The base looks like it's 2 seconds. The height looks like it's 8 meters per second. So that's the same thing as 1/2 times 2 times 8 meters per second times seconds. So it's pretty nice. The 2's cancel, the seconds cancel. It just becomes 8 meters. That big rectangle looks like the height is 8 meters per second. The width starts at 2, ends at 10, so also 8 meters per second. So 64 meters. That little blue rectangle, 1/2, or triangle, 1/2, 4. I'm going to be sloppy and not do the units just to move this along. So then this is 4 meters. The red rectangle looks like it's 2 seconds times 4 meters per second, so 8 meters. And then the blue rectangle at the end looks like it is 4 seconds by 4 meters per second. So 16 meters. So let's see, the blues add up to 20. So those both add up to 20 meters. So you got 20 meters, then you got 8 plus 8, which is 16, plus 64. This is 80. That is 100 meters. Equals the total displacement. I'm going to do one more. So I'm going to do number 54. A stone is dropped into a river from a bridge 43.9 meters above the water. Another stone is then thrown down vertically 1 second later after the first one is dropped. The stones both strike the water at the same time. What then must be the initial speed of the second stone? Then do a plot, which I'm not going to. So here's my picture. There's my bridge above water. Here's 2 people. The idea is that the first person just drops a stone down to the water. And then after a second later, this person chucks a stone down towards the water, and they hit the water at the same time. And this is 43.9 meters. What then must be the velocity? What was the initial velocity of the second stone? So this problem is essentially just two problems tied together. We could first talk about stone 1. And again, what do we know? We know it's, before I get to that, let's throw down a coordinate system first. So in this case, since I'm dropping things and going vertically, I'll have my coordinate system be vertical. Now I'll define up away from the water as the positive direction. Now I'll say my origin down here is the water. So the water corresponds to the origin, or your position equal to 0. And since often we use y instead of x when we're talking about vertical positions, we can use that here too. So I can say the final position of the stone is 0 meters. The initial position of the stone was, in this case, 43.9 meters above the origin where the water is. The initial velocity in the y direction in this case, the first stone was just released. So that's like me just holding out the rock and just letting go, not throwing it, not tossing it, just gently releasing it. So in this case, the initial velocity was 0. And now we have to bring back, we touched on this in the last lecture. When you're dealing with vertical motion, there is an acceleration that is always at play, and that is the acceleration from gravity. We, of course, have always all experienced gravity. If you just lift up your pencil now, hold it above your hand, and release it gently, your pencil starts stationary at v equal to 0. It ends with some non-zero value because it falls towards your other hand and hits your hand. So the velocity has changed. It went from being stationary to moving. So there must be an acceleration in the vertical direction. That acceleration we now know is from the acceleration due to gravity. And there was that YouTube video that you could have watched to see how you could actually go about measuring the acceleration due to gravity. And so, just as an aside here, the gravitational acceleration near the Earth being a key thing here. Don't do this on Mars. Don't do this way up in the atmosphere. Has a measured value of little g equal to 9.8 meters per second squared. I prefer, and the way I will do it in this course is I will always have little g as a positive number. Little g will always just be the number 9.8. It will never be negative 9.8. The negative is for you to determine and include in your equations if that makes sense for your given coordinate system. So when I go back to stone 1, I know the acceleration, it has an acceleration due to gravity, which I'll say is little g. But now you have to ask yourself, in your coordinate system, is it positive g or negative g? So in this case, since up is positive and gravity is pulling things down, I would say the acceleration from gravity is negative g, which is negative 9.8. Again, remember, I could have defined my coordinate system such that the positive direction was pointing down towards the water. In that case, the acceleration would not be negative 9.8. It would have been positive 9.8. It depends on your coordinate system. And then what do we want? I guess there are a couple things we could ask, maybe what is the t for it to hit the water? Because if we know the second rock hits the water at the same time, so then solving for the time it takes for stone 1 to hit the water would then be helpful. All right. Since this is a constant, this is great. I can use the kinematics equations. Now, I wrote down the kinematics equations using x, but since we're dealing with the vertical, they're just symbols. I could write it down like this too. I could say the final velocity or the final position equals the initial position plus the initial velocity in the y direction times t plus 1/2 the acceleration in the y direction times t squared. Since we're only dealing with one-dimensional motion, so the in the y direction might be a little redundant here. But just to make it crystal clear what we're talking about vertical heights, vertical motions and speeds through velocities, and vertical accelerations, all in the same one dimension. Now, is any of this zero that we can simplify our lives? The initial velocity was 0, so that kills this entire term. The final position is 0, so that kills that term. So then I could rewrite this as 0 equals the initial position, and now I will include the fact that a is minus g. Again, not plugging in numbers yet, but if I'm working in symbols, that's okay. But again, I prefer not to plug in numbers until the very end. Now I know this, I want this, but again, I have one equation with one unknown. Then if I solve for t squared, that is going to be 2 y0 over g. I could take the square root of both sides. That becomes t is plus or minus 2 y over g. So technically, there's two solutions or two values of t that will work. But I'm only going to use in this case the positive solution because the other one is going to be a negative time, which doesn't quite make sense for the problem that I'm using. So then I know then that t equals the square root of 2 y0 over g is my answer. And I think then if I did my math correct, this ends up being something like 2.99 seconds. So again, what does this mean? Interpret your answer. 2.99 seconds, the time it takes for the first stone, when released from rest, to make its way to the water. Can I do this all in the same one? I think so. So then stone 2, what do we know? Some things are the same. The initial position is the same. The final position is the same. The acceleration is the same. But now the initial velocity in the y direction is unknown. But we could say something about how long it takes this particular rock to make it to the water. Again, go back to the problem. It said that the second person waited 1 second and then threw their rock down, and it made it to the water at the same time as the first one. The first rock took 2.99 seconds. So then in this case, once they threw the rock, it was only 1.99 seconds until the rock hit the water. The kinematics equations do not apply, obviously, when the rock is in the person's hand. These are equations that only calculate how the motion is changing as it's falling from gravity. Similarly, these equations would not apply once the rocks hit the water, because the water would then start to push back on the rocks, and the rocks would in that case likely slow down once they hit the water, which would be an acceleration that is changing compared to when it was just gravity. So the kinematic equations would not apply. All right, so again, we have a similar kinematics equation. I could say the final position equals the initial position plus the initial velocity times t minus 1/2 gt squared. In this case, what do we know? We know this, we know this, we know this. Oh, sorry, we don't know that. This time we know time. Before we didn't know time, but we knew velocity. Now we don't know velocity, but we know time. I guess this is zero. Easier. So now it's solving for the velocity. So I could move the negative term to the other side. Again, I want this. So I could move 1/2 gt squared minus y naught equals v naught t, or 1/2 gt squared minus y naught divided by t equals v naught y. I know everything on the left-hand side. I could plug it in. Run out of room, so I'm actually going to fly over here. V naught y, if I plug in the numbers, when I did it, I got negative 12.31 meters per second. You might say, negative? Does that mean something is wrong? Well, no, think about our coordinate system. We initially threw the rock downward. We defined negative as downward. So the fact that the velocity is negative just means that the initial motion that the rock moved in was in the downward direction towards the water. You did indeed throw the rock down. If this were a positive number, that would have suggested that the second person actually threw the rock up into the air first before it came back down, which would have been a very strange solution given that the rocks hit the water at the same time. All right. I am tired. So I think those are a good set for now, and then we're going to do some more in class as well. But the kind of takeaways here is not just necessarily just the answers to the problems. Who cares about that, honestly? It's look more, if you review these a couple times, look at how I attempted and set the problems up. You know, I broke it down very systematically of writing down what I know, identifying relevant equations, keeping things as symbols and numbers only at the very end, justifying my steps along the way, and then actually doing the algebra or mathematics to arrive at the answer. And then once I get an answer, make sure that it isn't complete nonsense. All right, very good.